Morning, Mr. Kane.
Morning, Mr. Chi. How you doing?
I'm doing fine, thank you very much. How about you?
Oh, I'm doing all right. I'm just getting over a cold, so I should be maybe a little scratchy today.
All right.
All right, but we got to reach an equilibrium here, so let's move right on.
All right. Chemical equilibrium. The Unit 15 goals. Describe reversible reactions.
Wait. A reaction can back up?
Yeah, can be reversible.
Oh, cool.
I mean, you got decomposition and synthesis. They're the opposite of each other.
Oh, yeah, I guess they are.
So
you can make a reaction go one way or the other.
Yep. In a closed system particularly, you can do that. Understand and define equilibrium.
Okay, does equilibrium have to do with reversing reactions?
Yep.
Okay, so it's kind of like equilibrium on a teeter-totter, only.
Yes.
Now we're talking about equilibrium with a reaction, so forwards and backwards.
Yes.
Okay.
Recognize the system at equilibrium. You're going to be able to construct, calculate, and analyze the equilibrium expression and the value for the equilibrium constant, which is that KEQ.
So another thing you got to be able to do is calculate the equilibrium constant, which is a KEQ, or the equilibrium concentration of a reactant or product by using the equilibrium constant expression. So I think that's analyze, right?
Yes.
Same thing.
Analyze and calculate. Predict the result of making changes that affect the equilibrium position. This is called Le Chatelier's principle.
He sounds French.
Yep, French guy. All right, how chemical reactions occur. This is nice and easy. You have a collision model. The molecules must collide in order for a reaction to occur. And they must collide in the right orientation.
Right. So the rate at which a reaction happens is going to be dependent on the orientation, the concentration of the reactants, and the temperature.
Right.
Right.
Because, of course, the more you got, the more chance of a successful collision. The hotter the temperature, same thing.
The hotter the temperature, the faster they're moving, so the quicker they're going to hit each other.
Yeah.
And if you got the right orientation, then a reaction is going to occur for sure.
Correct.
Yeah. Concentration increases the rate because more molecules lead to more collisions.
Yep.
Right. Temperature increases the rate because you're moving faster.
Right.
Moving faster means that
more collisions.
More collisions. Okay.
Even at lower concentrations, with a higher temperature, you have the potential for more successful collisions.
And we got activation energy. It's the smallest amount of energy required for a reaction to occur. We can see here a graph of energy and the reactions process or progress. And you can see that this activation energy is listed right here as E sub A, or EA. It's the amount of energy needed to get the reaction to continue to make products.
Correct. Reactants are on the left, products on the right, and those reactants have to get over the hill, have to have a minimum amount of energy to get over that hill that is listed as E sub A. Activation energy.
So, Mrs. G, if I only had this much energy in the reaction would go up the hill, but then not be able
right back down.
Yeah,
Yep.
you can't go back. You can't go up and over. So it'd just come back down, and I'd still have reactants.
Yep. And at the top of the hill are intermediates that are called activated complexes.
Ooh.
And they either, if they have enough energy, they go down and make products.
Okay. If they don't, they go down the other way and they make reactants.
Yep.
Okay. All right. There's also a substance called a catalyst. Catalysts can speed up a reaction, and they don't wind up getting consumed. So they're not actually used by the reaction. They just facilitate it.
Correct.
Okay. And there are enzymes, which are biological catalysts, which our students are already familiar with because they talked about it last year in biology. And notice what a catalyst does is all it does is it lowers the activation energy. It creates a new curve.
Yep.
And makes it easier as far as energy is concerned.
It just creates a different pathway. It does not mess with the reactants or the product. Heterogeneous reactions. Go ahead, Mr. Kane.
All right. So there's two kinds of reactions, and you're gonna see both these terms. You probably are going to know these terms already. Actually,
yeah, they've seen this a million times.
Right. A homogeneous reaction is one where all the substances are the same because homo means the same.
Right.
And a heterogeneous reaction is where all the substances are not the same. And what we mean by the same here is we're talking about states of matter.
Right. You got all aqueous, okay, homogeneous. You got two substances aqueous, two of them gases, heterogeneous.
Okay.
End of story.
Yeah, and any combination of states of matter makes it heterogeneous.
Right.
Right. Even if it's
solids, liquids, gases, aqueous.
What if I had a reaction like this that said aqueous, aqueous, yields aqueous plus liquid.
That's a heterogeneous reaction.
Okay, so aqueous and liquid really aren't the same thing.
They are not the same thing.
Okay, just reinforcing that, hopefully. Equilibrium is the exact balancing of two processes, one of which is the opposite of the other.
Okay.
Like we say, kind of like being on a teeter-totter.
Yep.
Right? This shows a
Closed system
where a physical reaction is happening that is at equilibrium. 3 molecules evaporate and 3 molecules condense.
Right, you get a cycle going on.
Right. And if it keeps cycling the same way, 3 evaporate, 3 condense, 3 evaporate, 3 condense, 3 evaporate, 3 condense, you're at equilibrium. There's a balance.
Right, that's why you don't lose water out of a water bottle. It just keeps going back and forth, back and forth, back and forth, out of a closed water bottle.
Out of a closed water bottle, but if the water bottle breaks open,
Yep.
then it can
escape.
evaporate out.
Yep.
Nothing condenses back.
These are enclosed systems. Chemical equilibrium, a dynamic state where concentrations of all reactants and products remain constant and the rate of the forward reaction is same as the reverse reaction.
When we say that the forward reaction and the reverse reaction, we might say something like this: A plus B makes C plus D. If we want to show that they're both happening at the same rate, we often will draw the arrow, the reversible arrow, the same size, right?
Yes.
Okay, so if chemical equilibrium has been achieved, we draw that. If it hadn't been achieved, we might draw it more like this.
Yes.
Okay.
All right, so this is kind of just a visual aid for the equilibrium condition. This is concentration versus time. Reactants are the CO and the H2O. They are the green line. Notice that time is equal to 0, or initially. Lots of reactants, 0 products. As time progresses, concentration of your reactants go down, concentration of your products go up, and when you hit equilibrium, they flatline, meaning they are constant.
They don't change.
They do not change. They are constant. Not equal, constant.
Which is what that first statement says. The concentrations of all reactants and products remain constant, right?
Yes, correct.
And here's the second condition, right?
Right, here's the second condition, and another visual aid. The reactants in this point, and it's not the reactants, it's the rate of the disappearance of the reactants is in red, and the rate of appearance of the products is in blue. And initially, you'll have all reactants. They're going really fast. There's no products. And as time progresses, products start forming. And eventually, at equilibrium, they become equal to each other.
And the two rates are equal at that point in time.
Yep.
Which, that's what it says here.
Right.
Number 2, the rate of the forward reaction is the same as the reverse reaction.
Yep, 2 conditions have to be met for a system to be at equilibrium.
When a chemical reaction has reached equilibrium, we can write an equilibrium expression, right?
Correct.
Okay. And we usually call this equilibrium expression AKEQ, right?
Correct.
Okay. Writing the AKEQ isn't very hard. What we need to do is, number 1, write a balanced equation, which we can do. Number 2, we need to be able to write an equilibrium expression. An equilibrium expression simply does this. It places the concentrations. These square brackets here mean concentration. You might
Moles
want to
per
write
liter,
that down.
right, which is what we just did in the last unit, moles per liter.
Moles per liter. So place the product's molarity in the numerator. So products go up on top here. Okay, so like this. And we place the reactants in the denominator. And again, that is in a square bracket, so it's the concentration moles per liter.
Yep.
All right, in a heterogeneous reaction, we leave out pure solids and pure liquids. So you want to make a note of that we don't use solids and we don't use liquids.
As long as it's a heterogeneous reaction. If
Right.
they're all solids, then you have to use them.
Right, because there's nothing else.
Yeah,
So
there's nothing else.
if it's a homogeneous reaction, use everything that you're given.
Correct.
If it's a heterogeneous reaction, only use the gases and the aqueous.
Right.
Right. That's another way to say it. And then finally, we complete the equilibrium expression by using coefficients in the balanced equation as exponents for each of the concentrations. So for instance, if we were using the Haber process, which says that nitrogen gas and hydrogen gas can create ammonia gas, the balanced equation would start out as being this balanced equation, right?
Right, and it's homogeneous. They're all gases.
All right, I should point that out. So they're all gases, so it's homogeneous. So I will be using all of these in the equilibrium expression.
Correct.
So when I write my KEQ, it's going to be products first. So
concentration of ammonia gas
that's NH3
squared.
Ah, okay, and that's the exponents part,
Correct.
right?
That's the coefficient.
So that's step 3, is I'm putting the 2 as an exponent. Now I want to put nitrogen up here.
Raised to the first.
Raised to the first power, which is the same as just writing it.
Yeah.
And then hydrogen is going to be raised to the third power.
Now that's the equilibrium expression. Given the concentrations at equilibrium, we can calculate the value of big K.
The purpose of a KEQ, of an equilibrium constant, is to show if the reaction is favorable. If more products wind up being formed, then we get a larger numerator, right? Because products are on top.
Right, which is directly related to KEQ.
Right, because if products are on top and reactants are on the bottom, if products are more, you're going to get a bigger K.
Right, just look at the relationship, the mathematical relationship.
So a larger K means that I've got more products.
Right.
That's kind of a favorable reaction because usually we want to make products.
Right, if you're trying to feed the world and you're not making enough ammonia, if it's a real small K, what's the point of the reaction?
Right. Now, there's another way to look at this. If more reactants are formed, on the other hand, the denominator winds up being larger. A bigger denominator means that the KEQ is going to be small. So a small KEQ means that you don't have a favorable reaction.
Right. If the denominator is larger, that means the concentration of the reactants are larger. That means the concentration of the products are smaller.
Right.
They're kind of opposite to each other. Concentration of products and reactants usually are opposite to each other.
Because this is always considered in a closed system.
Correct.
So if you've got more reactant, then that means you've got less products.
Right.
If you've got more products, then you've got less reactant.
There are very few situations where they're equal.
Right.
Very, very few.
Well, if they're going to be equal, then both products and reactants are the same.
Right,
so you get a KEQ of 1, right?
That's correct.
Okay.
That's very rare.
I can algebra.
Yeah, how about that? Without a calculator.
So we got to write the equilibrium expression here, right?
Correct.
So the equilibrium expression is going to be KEQ is equal to...
Wait, now is it a homogeneous reaction?
No, it's not, because I have a liquid here.
I see a liquid. Okay, so
I don't include the pure liquid, right?
Right. Okay.
I do include the products, though.
It's going to be products over reactants.
All right, so I'm going to do concentration of the bicarbonate ion times the concentration of the hydronium ion. I need to write H2CO3, so I need to write that there. Okay. And they're all ones.
So that's the equilibrium expression, and given equilibrium concentrations, we can calculate the equilibrium constant.
Right.
Easy enough.
So we just have to put them in the right spot?
That is correct. So it would be... Oh, there you go. That was
like
easy.
That, right? So I put 1.19 times 10 to the negative fourth in place of the bicarbonate ion. I put 1.19 times 10 to the negative fourth in place of the hydronium ion because I was given both of those. It says here that this is equal to this, and they're both equal to that. And I divide by 3.3 times 10 to the negative second.
Okay, so you put it in your calculator, and you get an answer of 4.29 times 10 to the negative 7.
Now this is molarity times molarity over molarity, so molarity cancels, right?
Yeah, big K doesn't have units.
Yeah, so no units on this.
It is unitless.
It's just telling us 4.29 times 10 to the negative 7th. Well, that's a small number.
That's a really small number, so it's very reactant favored.
Right, so I wouldn't want to be making this if this was supposed to feed the world.
Right, if you were trying to feed the world on HCO3, you're not going to get anywhere.
Yeah, I guess using the phrase feed the world on HCO3 makes no sense.
No,
it makes sense
it
with ammonia, but not with HCO3.
The idea is if you were trying to make a lot of HCO3, this is not the reaction to use because you're not very product favored.
This is not the reaction we're looking at. All right, so some visual examples, guys, of KEQs. A very small KEQ might look like this. A very small KEQ, like 0.02. The idea is this. The arrow's pointing backwards at A and B because it's making more reactants than products. And if you look at the graph here, that's exactly what it shows. The reactance is much, much larger than the products.
It's very reactant favored.
Now, we had discussed this situation before, Mrs. G. What happens if the KQ is exactly 1?
That's very rare.
It's extremely rare, but then both reactions are occurring at the same rates,
Yeah.
which means that you'll get the same concentrations
Yeah.
of reactants and products, so you'll wind up with a 50-50 split.
Yeah.
It works, but it's not necessarily the greatest reaction in the world to
No.
do. A better reaction would be to do one with a very large KQ, like say maybe 50.
Right.
That one's definitely favored towards the products. And as you can see from the graph here, we're making a lot of product and
Right.
only leaving a small amount of reactant left
Correct.
over.